Alright, in this video I'm going to continue with some more examples of finding area bounded by polar curves. And this one we're just going to set up. I'm going to do two just basic setups, assuming you can take out your calculator. And then I'll do one where we need to actually compute it. So this is a cardioid. Again, the graph's provided. It's very rare on the BC exam you have to graph anything by hand. You just have to recognize what graph is which, but they try to make it as clear as they can. And so how does this cardioid get traced? Well, let me just kind of remind you so we can know the limits of integration. So theta r, so these values, your sort of common angles when graphing trig functions, this will produce one full graph. If you plug in 0 here, you get 2. You can check this. You get 4. At pi, you get 2. 3 pi over 2, you get 0. And 2 pi, you're back to 2. Okay, now if you plot these polar points, you'll note that this point gets traced when theta is equal to 0 and 2 pi. This point gets traced when theta is at pi over 2. Okay, this is a pretty standard and not too crazy polar graph. So our area is, remember, just to give you the general formula, it's 1/2 theta 1 to theta 2 r squared d theta. In our case, it would be 1/2. So theta 1 is just 0, okay, because we want the area inside the entire cardioid. And so, you know, the area is going to get traced in this fashion. I'll just use green here, right? As theta varies, your r value varies and sort of collects all this area all the way till you're back on the positive x-axis. So the integration limits are 0 to 2 pi. And then our r squared is just the curve squared. 2 plus 2 sine theta squared. 2 plus 2 sine theta squared d theta. Okay, again, we're just doing the setup. Okay, so there's one. Let's try a different example here. There's another cardioid. Find the area of the region in the first quadrant that is within this cardioid here. Okay, so again, I'm just going to kind of write down a couple of angles. When theta is 0, 1 minus cosine of 0 is 0. So that produces this point at the pole. And then at pi over 2, I get 1 minus cosine of pi over 2, which is just 1. So rotate pi over 2, walk out 1. And so that will produce the curve in the first quadrant, right? This area here is what we want. So our area, according to the formula, would be 1/2 0 to pi over 2 r squared d theta. And again, these can be done by hand. It's kind of tedious, and you need a lot of trig substitutions. I've got other videos where I do that, but you're not expected on the BC exam to do that. Okay, it takes too much time. It's not a concept that they expect you to know. But for your generic calculus knowledge, you know, go for it. This says find the area within the entire cardioid. Well, again, these cardioids get traced in a pretty standard fashion. So this point is going to be when theta is equal to pi. This point gets traced when it's 3 pi over 2, and you'll have one full rotation back at 2 pi. So it's the same integral, but our limits of integration are going to go from 0 to 2 pi. Okay, so you either do it by hand if you want to be heroic, or you take out a calculator and do that. So let's finish with one more with a calculator, and we'll do this rose petal graph again. We've done one in a previous video. Find the area of one petal of the rose petal curve, r equals 3 sine of 3 theta. Okay, so let's just say we wanted the area here. Okay, so like how does this get traced? Well, when theta is 0, since sine is 0, 0, our r value is 0, so it gets traced. Well, the first point is there. You know, if you're kind of trying to figure out how this gets traced, because remember, polar graphs can get traced in different directions. There are a couple ways to do it. Let's just assume you wanted to try to reason by hand. So like the period, if you think in Cartesian, the period would be 2 pi over 3, right? 2 pi over our b value. So if you do that, 2 pi over 3, and then just kind of cut that into fourths. Okay, if we can get another point, it might indicate basically how this is getting traced. So for example, pi over 6 we can tell is right here, right? That's going to be a petal tip. If I plug in pi over 6, this becomes 3 sine of pi over 2, which is just 3. Okay, so at pi over 6, it's going to be walking out 3. So yeah, so this is going to get traced like this. So like, the good news about a lot of these polar curves is they're very symmetric. So you could get the area of half of this rose petal, and then just double that, and then you get the area of a petal. You could also, let's just say you wanted the area inside a full petal. So we would need to know the second limit, the limit of integration that brings this polar graph back to the pole. And I think by my reasoning here, you can see it's going to be pi over 3. But let's just check. So that's 3 sine of pi, which is just 0. So yeah, at pi over 3, this polar curve comes back to the pole, and it'll produce one full petal. So those are my limits of integration. I'm going to assume, though, that you maybe just aren't as fluent in the reasoning I just did. And because most likely you will have a calculator to do a problem like this. So again, the strategy is to graph the rectangular or Cartesian. Okay, the rectangular or Cartesian. Oops. And we want to find an x-intercept, the first x-intercept after the original point. That'll give us our second limit of integration. So again, just our area by the formula is 1/2 r squared, which would be 3 sine 3 theta squared d theta. All right, so and then the lower limit of integration, I know we can tell it's 0. The upper limit of integration, we know it's pi over 3, but let's just pretend, you know, that you didn't have this nice polar grid with the angles, or you didn't use the reasoning I just did here. Then you're going to use a Cartesian graph and find that x-intercept. So let's do that. Okay, so again, graphically, it's, you know, as you rotate, we can see we're going to trace, and I think it's pretty clear that by 60 degrees we got a rose petal. But let's go here and do this by using the calculator. So I got my function, again my window. So I could tell that petal gets created before 90 degrees. So my upper limit of my upper x value is pi over 2. And then you just need your x and y min and max to accommodate the amplitude -3 and 3. You hit graph, okay, and you compute second calc 0.
Pull harder, Gordon. Show them the power of Pioneer Care. It's really important to us that our products are high quality and affordable. Would you ever know that this is fake?
Sorry. I keep telling you I have to pay for the paid version of this to get rid of that. So enter. Right, enter. So it looks like x is 1.0472. I'm just going to go record that. 1.0472. Okay, so again, in this graph, we had like just going to generically sketch it, right? If you take a look right? It kind of just it started it started at 0, went up to 3, and then like down to -3. It looks like crossing somewhere in the middle. So it's like it went like this, like that. Okay, we found that this value here was about 1.0472. We're going to store that as the letter B. We're going to put that B right here, and we're going to compute. All right, so let's go back to my graphing calculator here. So I'll go to my blank screen here. Again, X, hopefully it updated. Well, so it didn't update. This is weird. This calculator's funny. It should have updated your X value to be the most recent. I'm just going to put 1.0472. Let's just pretend this calculator behaved like it should have and store the exact most recent X value. Oops. I want to store that as B. Okay, and now we integrate 0.5 from 0 to B of what I have in y1 squared dx, and we get about 2.356. Okay, 2.356. And we are done.